All right, great, thanks. So everything I'll say today is joint work with Nick Anderson, who's in the audience. And so this the story starts with, I think, what we might all agree is one of the best functions in mathematics. So this is the Dedekind eta function. So this is the Dedekind eta function, and so eta of gamma tau is some 24th root of unity, chi of gamma times c tau plus d to the 1/2 times eta of tau. And this is true for gamma equals, let's say, A, B, C, D in the full modular group. Okay, so this is a basic building block for modular forms. So the inverse of the eta function generates one of the basic functions of additive number theory, so 1 over eta of tau. And so here's the Q expansion of eta of tau. This is 1 over q to the 124 times this infinite product of 1 minus q to the n. And these coefficients are p of n, and then q to the n minus 1 over 24. And so this is the partition function. And in case you haven't run into this, here's a definition by example. So 3 can be partitioned as 3 or 2 plus 1 or 1 plus 1 plus 1. And so this means that P of 3 equals 3. Okay, so these are very well-known things. So a long time ago, Hardy and Ramanujan developed the circle method to answer the question as to how big P of n is. So this is Hardy and Ramanujan. And so they proved that P of n asymptotically grows like e to the pi, and then there's it's like 2 root 2n over 3, and then a 4 root 3 times n. Okay, and so this method was perfected later by Rademacher, who obtained an exact formula for P of n. I'll write that down. So Rademacher proved that this is given exactly let's see, it's 2 pi divided by 24n minus 1 to the 3/4, and then an infinite sum of things which I will define in a second. But I'll write them down first. So an infinite sum, c goes from 1 to infinity. This will be some generalized Kloosterman sum, ac of n divided by c. And then there's an I Bessel function. So it's I 3/2 evaluated at basically the square root of n. So it's pi times the square root of 24n minus 1 over 6 times c, probably. Yeah, so let me tell you what these things are. So I secretly wrote, how'd that work? That worked good. So I secretly wrote some definitions on this board. So the Dedekind sum is the Dedekind sum which shows up in the definition of this multiplier chi. And this Kloosterman sum that we'll be interested in is something like an ordinary Kloosterman sum, but it's twisted by the exponential of this Dedekind sum. So that's what it is. And then the I Bessel function. So I'm going to try this experiment of using this as well. This is a picture of the I Bessel function. This is I 1/2. And so I 1/2 grows exponentially at infinity, but I 1/2 dies like x to the 1/2 at 0. Okay, so I 3/2 does the same thing, except it dies like x to the 3/2. Okay. So this is this exact formula. Thank you. And there's also, so this is an example of what I'd call a transcendental formula. There's also there's recently a beautiful algebraic formula due to Jan Bruinier-Ono. And so they proved the following. Again, I'll define these things in a minute. So P of n is given as a sum over certain quadratic forms, which I'll define in a minute. So it's a sum over some equivalence class of quadratic forms by the action of a congruent subgroup. And it's some function, which I'll define, evaluated at a point in the upper half plane. So again, in the interest of saving time, I'll just show you these things. Thanks. So this is the set of quadratic forms. I mean, these are quadratic forms of discriminant 1 minus 24n with some extra conditions. And this is the function p. So it's a non-holomorphic modular function. And tau q denotes the root of the quadratic form q, which lies in the upper half plane. Okay. So we have these two formulas. Okay, so now I'd like to introduce you to another of my favorite functions, which I think is, so the eta function, or 1 over the eta function, is kind of a prototype for weakly holomorphic modular forms. And I think this guy is kind of a prototype for Mach theta functions. Okay, so I'll start with the combinatorial definition. So this is the smallest parts function, which is in the title. Smallest parts function. So this is written SPT of n. And so SPT of n is the number of smallest parts in the partitions of n. So the number of parts in the partitions of n. Okay, so this was introduced a while back by George Andrews, so I should write his name down. And again, by way, this may strike you as a fairly strange definition. So by way of example, so 3 is 2 plus 1, 2 plus plus, no, it's 2 plus 1, which is 1 plus 1 plus 1. And now we want to count all of the smallest parts. So this guy here, 1 plus 1 plus 1, the smallest part occurs 3 times. So that contributes 3 to the count. Here the smallest part only occurs once. And here the smallest part occurs only once. So if I count up the arrows, I find that SPT of 3 is 5. Okay. And you may think that this is some strange combinatorial definition. I won't argue with that. But the function which it generates has some beautiful automorphic properties, which is mostly what I'll be interested in. So let me write that down now. So if we sort of complete the generating function like this, so if I define a function f of tau as sort of the generating function for SPT, minus plus a sort of a derivative of the generating function for partitions. So it would be plus 24n minus 1. I think it's divided by 12 times the sum p of n, q to the n minus 1 over 24. Yeah, that's not good. Yeah, let's go with negative 1/12. Man, oh, you know what I need to do? I need to put that inside, yeah. Okay, so that would fix it and make it correct probably at the same time. So let's try this, 24n minus 1 over 12 times p of n times q to the n minus 1/24. And then there's this non-holomorphic term. There's a constant, I think it's root 3i divided by 2 pi. Then there's an integral of the eta function, eta of w over tau plus w to the 3/2, and a dw, and so this should go from like minus tau bar to I infinity. Okay, so this is going to be a Mach modular form of weight 3/2, and so the fact, which was proved by Brinkman, I think you might also find it, you could get this from a paper of Zagier, is that f of gamma tau transforms like a modular form of weight 3/2. So it's chi of gamma. This is the same chi which appears over there, but with a conjugate times c tau plus d to the 3/2 times f of tau. And so this is true for all gamma. Right, and so this part here is something that we've heard about several times during this conference. So this is a Mach theta function of weight 3/2. And it's one of the nicest ones I know, particularly because the shadow is the nicest modular form I know, which is the eta function. Okay. So there's that. So you could ask questions about asymptotics. Again, Brinkman worked out the asymptotics for this function using the circle method. You could ask about arithmetic. There are some papers by Ken Ono and myself and Katrin and Jeremy and myself and Byung Chan, who's also here. And Amanda Folsom, right? Sorry. About that. That's not what I want to talk about today. So we checked Wikipedia today, and it says there is no closed formula for SPT of n. So I was disappointed that this was not automatically updated when we proved this theorem, but it wasn't. So what I'd like to tell you is some formulas for SPT of n. And there is, yeah. So, and I had thought that Wikipedia was always correct, but this turns out. Okay. So anyway, I want to write down two theorems. So theorem one, this is a formula which closely resembles Rademacher's formula. So it goes like this. So SPT of n it's pi over 6 times it's 24n minus 1 to the 1/4. And then a similar looking sum. So it's a sum as c goes from 1 to infinity. It's AC of n over c. And now I get a difference of I Bessel function. So I get an I 1/2 minus I 3/2 evaluated the same thing, which is pi times the square root of 24n minus 1, divided by 6c. Okay, so this looks quite a bit like Rademacher's formula. And maybe I'll try to sneak in theorem 2 here as well. So there's the transcendental formula. And so the algebraic formula resembles this formula that's over here. So SPT of n is sum over the same quadratic forms. So 1 minus 24n mod gamma 0, 6. And now there's a difference of two functions. So it's f of tau q minus p of tau q. And I just remembered that I forgot some normalizing factor in both places. So let me fix this one first. So this should be 1 over 24n minus 1. And then this guy, I think, should be a 12th. Okay. Okay. So there are the theorems. And, of course, the most natural thing is not SPT, because that's part of a Mach theta function, which is more natural. So the more natural formula would be for this whole thing, and the effect of that would be just deleting these negative signs.
Sorry, can you say what F was?
Yeah, oh, that's coming up. Yeah, that's so. I will. This is F. So F is a modular function on gamma 0, 6.
That's capital F.
No, this is little f. Uh-oh. Ah, there it is. Okay. So there it is. I mean, it's just a modular function which has some obvious nice properties, like under the Akin-Lehner involutions. So while I'm here, I can give you an example of this theorem, the bottom one. And so you can evaluate these things. You can find the defining polynomials of these algebraic numbers. Unfortunately, I think the only time that the polynomials you get are solvable were n equals 1. So you get one example that can be written down using, with radicals. And so there it is. Oh, it's up here. Yeah, so this is, SPT of 1 is this, and that's that, and that's that. So there's that formula. Okay. So I'm going to turn that off now.
Note that SPT of 1 is actually equals 1.
Yeah, that equals 1. Yeah. Actually, it has to equal 1. There's some Galois action on the cube roots of unity. So it's a little more, it looks a little more exciting than it actually is. So I probably shouldn't have told you that. But again, we can't compute anymore because the next one is like a degree 7. And so you can just say it's a root of this polynomial. Okay. So yeah, I want to talk, well, I want to say some words about the proofs. Before saying some words about the proofs, I want to talk about this is an infinite series and it should converge. So let me say a few words about that. So yeah, the question is about convergence. So there's a trivial bound for these Kloosterman sums, so that AC of n is less than or equal to C, and this is actually enough to prove that Rademacher's formula converges. So this implies that Rademacher's formula converges. There's a Weil type bound. For example, Lamer proved that AC of n is bounded by, so as c goes to infinity, this is bounded by c to the 1/2 plus epsilon, independently of n. So this is quite nice. But this actually isn't enough to prove that this converges. I mean, the I3/2 is no problem, but the I3/2 is like c to the -1/2, and then there's c to the 1/2, and you're left with 1 over c plus a c to the epsilon. So this is not enough for convergence. And so you need some kind of power savings, not in the Kloosterman sums themselves, because this is the best you can do for individual Kloosterman sums. But in sums of Kloosterman sums. So here's a fact, which I'll return to a little bit later on. And so the fact is, for positive n, there's a significant savings in the sums of Kloosterman sums. So sum c is 1, sum over c less than or equal to x of AC of n over c is, so it's at most, it's like x to the 1/6 plus epsilon. Okay, where this implied constant depends both on n and on epsilon, and this is plenty to give you convergence. So this implies convergence. Okay, so there's that, and I'll talk some more about this a little bit later on. Okay. Yeah. So. Touch that. So I'll talk a little bit about the proofs. So we proved the Theorem 2 first, actually, and then used Theorem 2 to deduce Theorem 1. So I'll say a couple of words on the proof, and I'd like to thank Stefan Ehlens for his beautiful talk this morning, in which he gave a lot of the tools for the proof of Theorem 2. So this relies on the theta lift, which, as we heard this morning, is a big, beautiful, and useful machine. And this theorem follows more or less directly from an application of a theta lift of Bruinier and Funke. Okay, so I think in the language of this morning's talk, probably n is 3, something like that. Okay, so the proof of the algebraic formula, so the proof of Theorem 2. We use this theta lift of due to Bruinier and Funke. Okay, I won't say too much about this, but I will say that if f of z, So this is our f of z, which was called f of tau before. So f of z was this modular function of level 6. Then there's a theta lift, which is called, I'll call it I of tau f. And so you get this by integrating over the modular curve, which was discussed this morning. And you integrate f of z against some kind of theta kernel, and it's actually this Kudla-Milson theta kernel, so tau and z. So this is the non-holomorphic one. It produces something non-holomorphic, and this guy decays very rapidly and is able to handle the singularities of f of z at the cusps. And then the facts, which are true about the theta lift, are, so here are some facts. So I guess, two facts. The first is that I of tau f, this guy is a harmonic Moss form. So it'll be of weight 3/2. For the some Weil representation associated to gamma 0,6. Okay, and the coefficients are given as traces of this modular function over the CM points. Okay, so the traces, the coefficients are traces of f over CM points. Okay, and so really what we have to prove is just prove, this is a vector valued thing, and it turns out that the first component of this equals what I called capital F of tau, and which was written up here. So you want to prove that the first component of this theta lift is equal to capital F of tau. Okay, and this is basically the proof of this algebraic formula. So it's similar to the proof of the proof of Bruinier-Ono for this the algebraic formula for P of n. Okay. So that's how that goes. So for the proof of the transcendental formula, yeah, we'll erase this. Yeah, so for the proof of Theorem One, as I said, basically starts with Theorem Two. So here's the proof of Theorem One. So what we do is we basically need some way to write down these values. Okay, so we construct some Moss-Poincare series which sort of want to be f of tau. Okay, so to be vague, we construct a linear combination of Moss-Poincare series so I'll call this f of tau s, such that f of tau 1 really looks like f of tau. Or let me write it this way. Let's say this should be f of tau. These guys only converge at the outset for the real part of s bigger than 1. Okay. And then there's quite a bit of work, and this involves the Ahlgren involutions and so forth. So some work. implies you can write down sort of a Fourier expansion for these guys. So f of tau s. There's some terms that I don't really want to talk about. And then it looks, this is how it comes out. It comes out as 2 root y times a sum over non-zero n, and there's some coefficients. So as of n, and then some k-Bessel function, maybe ks minus a half, 2 pi, absolute value of n and y, and then maybe an e of nx. All right, so this is how they come out. I'll show you just so you can see them. What the, yeah, so this is what the ASs look like. So these are ordinary Kloosterman sums, S of M and C, and the AS are sums of these ordinary Kloosterman sums weighted either by I Bessel or J Bessel functions. Okay, so they go in here, and so. But this is quite explicit, and so this gives, you can prove that there's an analytic continuation. So you get an analytic continuation to the real part of S bigger than 3/4, I think. And using this, you can then prove that f of tau 1 indeed is f of tau. So we have some explicit formula involving Bessel functions, which represents this function. And so now it's sort of, you feel like you might be in the game to try to prove something like that.
So mu is the Mobius function?
Yeah, mu is the Mobius function, right, yeah.
And what is the connection to smallest part from in the proof of Theorem 2 on this side? Theorem 2 you constructed some detail and you say it's the same as f. F was defined as smallest part.
F was defined. This F?
So the capital F of tau.
Oh, the theta lift of little f equals capital F, and that's the connection.
Yeah. You didn't give the argument.
No, it's not obvious. Yeah, it's a sketch of the proof. Yeah, I mean, you can compute what the theta lift is, and the function f is constructed so that the theta lift of f little f equals capital F. But no, it's not obvious.
You know, it's a harmonic mass point.
It's in the same space.
Okay, so difference is 0.
Yes.
Yeah, no, there's quite a bit that goes into that board. Yeah. Okay. Yeah, so there's that, and so I mean at the end of this, so. So I guess so this, I mean this, I'm sort of plugging this, what I just wrote down into this formula would give SPT, I guess, as a limit, right? So SPT of n is some kind of limit so it would be a limit as s goes to 1 from the plus side, and then it's pi over root 12, is that right? Okay, so these constants don't matter so much. And you get some sum that looks like this. So it's like c to the negative half and an I Bessel function of same thing. So pi root 24n minus 1 over 6c. And then some character sum. So say maybe b mod 12c. And this guy is defined by some quadratic conditions, maybe 1 minus 24n mod 24c. And there's some character, like 12 over b, and then e of, this must be b over 12c. Okay, so I think this is right. And this, as I said, doesn't matter so much. And then you have to do some work with the character sums, and then really want to interchange the limit and the sum, and so you need some uniform convergence, and that comes out of this bound for sums of Kloosterman sums that I wrote down. So so the sort of bounds, the bounds for sums of Kloosterman sums implies you can move the limit inside, basically. And that, plus some work with the character sums, gives this theorem. So that's how that goes. So I guess in the remaining time, I want to talk a little bit about this bound for sums of Kloosterman sums, which I also think is interesting. So let me write down the definition. So Sn of x is going to be the sum over c less than or equal to x of a c of n over c. Is that right? Yeah. And yeah, let me show you some pictures of the size of this. So remember that, okay, well, I'll just show you some pictures. Okay, so these are some graphs. So there's S1 of x. So this is out to 10,000. You'll notice it's hovering at a little below 0.5. There's S2 of x. It's a little bit bigger, but not much. And then there's S negative 1 of x, which looks quite a bit different. And S negative 2 of x, which looks also a bit different. So now you might guess a pattern. There's S negative 3, S negative 4, and then there's S negative 5, and S negative 7. Okay, so these are interesting pictures if you've never seen them before. And so some of them are very small, and some of them look like they're growing like the square root of x, and that's exactly the truth. And basically, these grow like the square root of x every time there's a coefficient of the eta function. So these numbers, well, the negatives of these numbers, 7, 5, 2, and 1, are exactly the pentagonal numbers, which are exactly the coefficients of the eta function. And that's where you get something like plus or minus the square root of x. And otherwise, you get this sort of random noise. Yeah, so those are the pictures. So good. So let me write down a theorem. So the theorem, here's a theorem which explains these pictures. So the theorem says that if minus n, if minus n looks like k times 3k plus or minus 1 over 2, and these are what we call the pentagonal numbers, so this is pentagonal, then this sum Sn of x looks like, well, the constant's minus 1 to the k times 4 root 3 over pi times x to the half, and then plus a big O of x to the 1/6 plus epsilon, and the big O will depend on n and epsilon. And if negative n doesn't have that form, so else Sn of x is just this guy is big O and epsilon of x to the 1/6 plus epsilon. So yeah, so this is written down by Brueggemann, and I mean this follows like an argument of Goldfeld and Sarnak, and I'll say a few words about how this goes. So basically, so this has to do with Moss cusp forms for the eta multiplier. So these are Moss cusp forms of weight 1/2 on SL2Z for the eta multiplier. So let me write down what these guys are. So the space is L2 of H mod SL2Z. And there's a character, and the weight is 1/2. So the main thing that these guys do for you is that f of gamma tau is chi of gamma times, and I think it's c tau plus d divided by absolute value of c tau plus d to the 1/2 times f of tau. Okay, so there's this standard differential operator, delta 1/2 on this space, and this has a real positive spectrum. So this has a real positive spectrum, and sort of the quality of these bounds for Kloosterman sums have everything to do with the sort of distribution, the distribution of this spectrum. So let me draw a little picture. So the smallest eigenvalue is the one that comes from the eta function itself. So there's this minimal eigenvalue called lambda 0, and this turns out to be 3/16 in weight 1/2. And the Moss-Kuss form that gives you this eigenvalue is u0, and this is it's y to the 1/4 times eta of tau. And then the rest of them are spread out. So there's a lambda 1, and there's a lambda 2, and there's a lambda 3, and so forth and so on. Okay. And so there's an Invenciones paper of Goldfeld and Sarnak from the mid-'80s, which gives you something like this. So Goldfeld and Sarnak, so their paper tells you that Sn of x is it's some constant. So let me call it Cn, C sub n, times x to the 1/2, plus big O of, let's say, x to the 2s1 minus 1, plus big O of x to the 1/6 plus epsilon. And I should tell you what S1 is. So, so lambda j is Sj times 1 minus Sj. It's sort of this parameter. Okay. And then Cn can be computed explicitly. I mean, this comes from computing the inner product of some Moss-Poincaré series in a couple of different ways, and that produces the constant. And then the fact is that this number here, 2s1 minus 1, is less than 1/6 plus epsilon, and this corresponds to lambda 1 being big enough. Okay, so the fact. So the eigenvalues below a quarter are exceptional. It turns out in this case there are no exceptional eigenvalues, and that's enough to do it. So the fact is that 2s1 minus 1 is bigger than 1/6. Oh, sorry, no, less than 1/6. Okay. And as I said, so this was proved in a long paper of Brueggemann in the 80s. We've written down a proof which involves sort of lifting to Moss-Kuss forms of weight 0 on gamma 0/6. Sort of it's an argument like the Shimura lift, following Niwa's paper. If you want to use a huge hammer, this would also follow from like the Kim Shahidi paper about Langland's functoriality for the symmetric cube of GL2. So that would be enough to push this out, but that's probably a bit of a huge hammer to use for this. But in any event, this gets swallowed into the error term, and that's what happens. So that's a sketch of that. So to finish up, I'd like to say a few more things. Some things we're thinking about now. Kind of like to have that back. No. Here we go. Yeah, so I think it's clear from the pictures that the correct exponent is probably not 1/6. And so one of the things we're thinking about now is what the true size of Sn of x is. So this is sort of current question. What's the true size of this guy, Sn of x? Yeah, that's coming. Yeah. Yeah, so for the ordinary Kloosterman sums, right? So for the ordinary Kloosterman sums, there is this famous conjecture of Linux. I'll write it down. So there's a Linux conjecture. And this says that some C up to x, S of, well, okay, M and C divided by C. So I think the original conjecture says this is less than x to the epsilon. There's a paper, Sarnak and Zimmerman, where they give a convincing argument that this needs to be sort of given this, they call it a safety valve in M and N. So this is sort of likely the truth for the ordinary Kloosterman sums. So this is a conjecture. And then there's a famous result of Kuznetsov. I feel like I've spelled that incorrectly. Yeah, that's what I have. So there's a theorem which gives this. So C up to x, S of MNC divided by C is less than, and I think he gets x to the 1/6, and then a log x to the 1/3. Again, this constant depends on M and N, and I think he can make this explicit. And then there's the recent paper which I just mentioned by Sarnak and Zimmerman. So, and I won't write down the bound they get for the ordinary Kloosterman sums, but it makes much more clear the dependence on M and N, and it also separates dependence additively rather than multiplicatively. And the quality of their bound also depends on sort of progress toward the Ramanujan conjecture for GL2. And so one of the things we're thinking about is whether or not it's possible to adapt those methods to try to get better bounds for these generalized sums of Kloosterman sums. So that's something I hope to maybe tell you about next time. So thank you.